So when we talk about stoichiometry, again, this is going to be a recap. So I'm going to go over the most important stuff. But the most important thing is this concept of what exactly is a mole. A mole is just a collection of particles, and it's a collection that's quite big. Okay, 6.02 times 10 to the power 23 particles. That makes up 1 mole. This number is also known as Avogadro's number, and we have a formula that we can use to calculate the number of mole based on the number of individual particles. Now remember that this 6.02 times 10 to the power 23 is the number of particles per mole, and those particles can be anything from atoms to molecules to ions. Really doesn't matter what thing I'm talking about. It would just be 6.02 times 10 to the 23 of that specific thing would make up 1 mole. Just like a dozen eggs and a dozen cupcakes both mean 12, right? So we are going to come across this equation a little bit later today. Most of the calculations that we do in terms of mole is when we actually are given substances in terms of mass, and then we have to do the conversion to mole. The reason why most of the time it will be measured in mass is because mass is the easiest way to measure out an amount of stuff. There's no fancy scale in the lab that's going to measure the amount of mole. So when we measure out our chemicals, it's usually done in terms of mass. However, when I'm looking at the way particles are reacting and the ratio that the particles are reacting, it's always going to be based on the number of particles. So whatever I have in mass, I'm going to have to convert that to mole first before I can apply that concept, before I can work with that amount of stuff inside of a reaction. Right. So one of the most common conversions that you'll be doing is from mass to mole. Here we distinguish between 2 types of mass. So we have the mass of the sample, right? That's the lowercase m. So that would be, for example, we have 15 grams of oxygen. So how much of this specific substance do you have? The capital M that goes at the bottom, that is the molar mass that comes from your periodic table, right? So that's the biggest distinction between those different masses. I don't think you really need to be taught again how to calculate molar mass, but it's basically just the sum of the molar masses from the periodic table. So if I have calcium sulfate, that's 1 mass of 1 calcium plus 1 sulfur plus 4 oxygens, so 4 times 16. If I'm calculating the relative mass, there will be no units. If I'm calculating the molar mass, then the unit is simply grams per mole. But the way that I do the calculation looks exactly the same. Again, I'm not going to go through too much on that. All right, percentage composition. So if I want to know what is the percentage that a specific element, how much of a substance, okay, is made up of a specific element. So let's say, for example, I have aluminium. Oopsie. So let's say I've got aluminium oxide. Okay, and I want to know how much aluminium is inside of this aluminium oxide. That's when I will be expressing the aluminium content as a percentage. It's important to note that this percentages in all of the calculations that we're going to be doing, these percentages are done in terms of mass. Okay, it's always in terms of mass. So if I want to know what is the percentage of a specific element inside of a compound, I will be doing that using the molar masses. So here's just 2 examples. So if I look at iron oxide, iron 2 oxide, there are 2 iron particles. Okay, so that means that it's going to be 2 times 56, which is the iron, divided by 160, which is the mass of the entire molecule. And I multiply that by 100 to convert that to a percentage. If I look at the magnetite, there's 3 iron particles or 3 iron atoms in this molecule. So it will be 3 times the mass of iron divided by the total mass of the entire molecule, right? Multiply that by 100 and express it as a percentage. Why do we want to do this? It's so that we can compare the amount of the amount of an element inside a compound, that we can make that comparison. So in this case, we've got 2 samples of iron oxide, and we can actually compare which one contains more iron, and we're expressing that as a percentage. All right. Okay, then just in terms of the different types of chemical formulae, especially if you are in the IEB and you've done some structural formula, this would be applicable to you. Basically, when we talk about molecular formula, we are referring to the formula or the ratio of the actual molecule. Okay, so if it's C2H6, that tells you exactly 2 carbons, 6 hydrogens inside of this compound. If I look at the empirical formula, that will be the simplest whole number ratio of the atoms. So in this specific case, if I look at C2H6, that's the actual ratio, but that can be simplified to a 1:3 ratio in terms of my carbon and hydrogen. So all you need to remember here is that when we're talking about the empirical formula, we are referring to the simplest ratio. And when we're talking about the molecular formula, it is the actual ratio in that molecule. Structural formulae, for those of you who have used it by now, that is just a way for us to show how things are bonded together. So by just expressing it as C2H6, we are indicating the atoms that it's made up of, but not necessarily showing any bonds. By using a structural formula, we can also show the bonds that are present. Are they single bonds? Are they double bonds? And between which 2 atoms are those bonds being formed? All right. The other conversion that we'll be doing a lot is the conversion of concentration and mole. Now, there are two phases for which we use concentration. We use concentration for aqueous solutions, all right? And if we're talking about the concentration of an aqueous solution, then the N will be the amount of solute. All right, so in the case of, let's say, a salt solution, that would be the sodium chloride, the number of moles of sodium chloride. The volume would be the amount or volume of the solvent, which again in a salt water solution, that would be the water. Okay, so if I'm looking at the concentration of, for example, a sodium chloride solution, it would be the number of moles of the actual salt divided by the volume of the water that salt was dissolved into. All right, so that's how we would determine concentration of a solution. It's important just to note the terminologies here, right? It's a solvent. That's the liquid that you dissolve things into. It's usually water, but we can also dissolve things in alcohols, right? The solvent simply refers to the liquid that this substance is dissolved into. The solute, okay, the solute, that is the substance that you are dissolving into that liquid. So that could be a solid, like for example, a salt solution, but it can also be a gas. Okay, we can dissolve gases into liquids, like for example, cool drink, these little carbon dioxide bubbles that's been dissolved into some liquid. Right. We can also do concentration of gases. We can also calculate concentrations for gases, okay, with exactly the same formula. The N would now refer to the amount of gas. And if it's a gas that's not dissolved, then the volume would refer to the volume of the container. Okay, so concentration of a gas, we'll use the volume of a container. Concentration of a solution, we use the volume of the liquid that the solvent, the solute is dissolved into. Okay. We just need to be mindful that these volume values needs to always be in cubic decimeters. So if we are given volumes in cubic centimeters, we need to do that conversion. And to go from cubic centimeters to cubic decimeters, we divide by 1,000. So that's the conversion. All right. And we always need to be working in cubic decimeters. Okay. So we've covered now the conversion between mass and mole, and we've covered the conversion between concentration and mole. The third conversion that you need to be very comfortable with is the conversion between volume of a gas and mole. Okay. Now, the volume of a gas will be determined by its pressure, the number of particles, and the temperature. We deal with those extensively in gas laws. But what we do need to know is that as long as these gases have the same volume under the same conditions of temperature and pressure, they will have the same number of molecules. In other words, the same number of moles, right? And that is a law that we need to know and we need to be able to use. Normally, if we are dealing with gases at STP, standard temperature and pressure, then that volume would be 22.4 cubic decimeters per mole. So each mole contains or occupies a volume of 22.4 cubic decimeters. This is only true at STP. So if we are ever given a situation where there's temperature or pressure that's not standard, then we're going to have to take a little bit of a different route, like what we cover in gas laws. Okay. If we know that this volume or this gas is at STP, we can use 22.4 mole per cubic decimeter per mole. But what we do find is that sometimes they will give us a different molar volume. All right. So sometimes they will say it's at 25 degrees Celsius, and at this temperature, the molar volume is 25. Then you'll just use 25 instead of 22.4. So just be aware of that in the questions that you're going to answer. If I want to do the conversion now between the number of moles, and volume, then I can say the number of moles is equal to volume divided by the molar volume, where V is the volume of the gas, and the molar volume will be 22.4 cubic decimeters per mole at STP. Okay, it will be a different value at a different temperature and pressure, which will either be communicated or you'll have to calculate using the ideal gas equation. Now, because all gases under the same temperature and pressure conditions occupy the same volume per mole, it means that when I look at molar reactions, I can look at them in terms of the number of moles, but I can also look at them in terms of the volume in which they react. So if I look at this balanced equation actually says that 1 mole of, okay, Pierre, I'll check your question in a second. I lost my train of thought. All right, if I look at this balanced equation, there's a 1 in front of this nitrogen. So what this means is that 1 mole of nitrogen reacts with 2 moles of oxygen to form 2 moles of nitrogen dioxide. Okay, that's the molar ratio. But we know that 1 mole of any gas will occupy the same volume. So regardless of whether I'm talking about a mole of nitrogen or a mole of oxygen, the volume that 1 mole occupies will be the same. So therefore, I can also treat my volumes in that same ratio. Okay, so 1 cubic decimeter of nitrogen will react with 2 cubic decimeters of oxygen to form 2 cubic decimeters of NO2. Okay, or 22.4 cubic decimeters of nitrogen reacts with 44.8 cubic decimeters of oxygen to form 44.8 cubic decimeters of nitrogen dioxide. So what I'm trying to emphasize here is that for reactions where I only have gases, the gases will have the same volume ratio as the balanced equation ratio. Okay, I'm just going to quickly check the chat here, Pierre. Your question says the only thing that changes in the container is the volume. The only thing that changes in the container is the volume. Pierre, I'm not quite sure what you're asking there, buddy. You either gonna have to type it out again, or feel free to unmute. Okay, so if you have a box full of gas and you press down the lid and the space decreases. Yes, okay, if I change the pressure, if I'm changing the pressure, it's only the volume that changes. Okay, yes. If I'm changing the pressure, only the volume changes. Or if I change the pressure, but I keep the volume the same, then it's the temperature that changes. That's gas laws, right? So that's, I think tomorrow, I'm not sure exactly when you're doing gas laws, but we deal with extensively in gas laws. But ultimately, if I change the volume of the container, if I change the pressure or the volume or the temperature, those things will have an effect on each other. The gas particles mix or combine. Yeah, so these gas particles, the nitrogen and the oxygen, these will actually bond together to form a new molecule. Right. So that's why the volume, you can't just say 22.4 cubic decimeters plus 44.8, and now you think the volume should also be combined. Okay, because these molecules now go and they kind of stick together, so they're occupying less space under the same pressure and temperature conditions. I hope I clarified that for you. If not, then we'll have to readdress that. Okay. Right. So just once again, this molar volume, whenever I want to convert from volume to mole, then I'm going to be using this equation. Molar volume is usually 22.4. But please be aware, and we'll get an example, we'll see an example like that in the past paper questions. There are situations where we give you volume or a new molar gas volume, okay, where it's not 22.4. We'll see that in the example questions that we're going to go through. All right. Water of crystallization. So for the kids that are doing the DBE, so IEB, you don't do this, but DBE, the water of crystallization is when you have ionic substances, which then have ions which have come together. And as these ions come together, they form a little crystal lattice. And inside of that crystal lattice, between all of those ions, when these ions come together, it forms like a little crystal lattice. And on the inside of that crystal lattice, it's got a little cavity. And inside of that cavity, there's little water molecules that are captured there. So that is known as the water of crystallization. Ionic substances come together, form a crystal, and water gets captured inside of that crystal. Now, when we write out the formula for water of crystallization, we would normally represent it like this, okay? We would say copper sulfate or whatever the ionic substance is, and then a dot. Now this dot is not a multiplication dot, but rather shows you that there is now a very light bond between the water and these copper sulfate molecules. So it shows you that this is captured inside of the ion. And then there will be a ratio of the water molecules per formula unit of your ionic substance. Okay, so in this specific case, my ratio of copper sulfate to water will be a 1:5 ratio. Okay, of course, I'm going to need a lot more copper and sulfate ions to form a lattice than just those two. But once I've got a lattice formed out of a whole bunch of copper ions and a whole bunch of sulfate ions, the copper sulfate and the water will be in a 1:5 ratio. So please understand that this is representing a ratio of ionic substances to water. So if we want to determine what that value is, we want to determine this value, then we've got to start by separating those two from each other and then working out what is their molar ratio. So for example, here we have 13.2 grams of zinc sulfate, which has been hydrated. So this 13.2 grams would be the zinc sulfate and the water. Okay, that's the mass of all of this together. Now they want us to calculate, if I've heated up this sample, and I heat it up because I want to evaporate the water that's captured inside. So if I heat it up and I heat it up and I heat it up, and there's 7.4 grams of solid which remains. This 7.4 grams now has no water in it because all the water has been evaporated from heating it up in that crucible. Okay, so we've got to take the sample that we've got, and we've got to separate that out between the water and the zinc sulfate. So we can see then that there will be 5.8 grams of water that has been liberated. 13.2 gram sample with 7.4 grams left after all the water has been removed. Now remember that this water of crystallization, for which I'm trying to find that X value, that is simply a ratio. So I actually now need to go find what is the ratio between the zinc sulfate and the water. Now, when I talk about ratios, those ratios must be in terms of the number of particles. So at the moment, I have mass of zinc sulfate and mass of water. I can't put masses in ratios. I can only put moles in ratios. So I need to go and I need to convert that to mole. Okay, so I need to go and figure out how many moles of water does this 5.8 grams represent. And I need to do the same for the anhydrous salt. Anhydrous means without water. So that zinc sulfate, the 7.4 grams that's left over, I have to go figure out how many moles does that represent. So now I know the number of zinc sulfate particles and I know the number of water particles. And now I can get a ratio. Ratio needs to be in terms of mole, cannot be in terms of mass. So to get this ratio, I can either say mole of water divided by mole of anhydrous salt, and that will give me a ratio of 7, okay, which means there's 7 times the water in terms, or 7 times more water than the ionic salt, okay? The other way that we can do this is simply to say that the zinc sulfate in ratio to the water is a 0.046 to 0.32, 0.32, okay? So that's number of mole of zinc in ratio to number of moles of water. And then to simplify it, I just divide by the smallest number in that ratio. Okay, so I'm going to divide both sides by 0.046, and then I'm going to get a 1:7 ratio. All right. I want to simplify this ratio. That's why I divide it by the smallest ratio number, and then I'm going to get a ratio number of 1 to something else. Okay. If you've done this calculation, now let's say by some miracle, you've divided by the smallest number and you've got an answer that looks like this. So you've divided by the smallest number, and this answer is a 1 to 3.5. Okay, what do we do now? This 3.5 means there's 3.5 water molecules. That doesn't make sense. I cannot have half a water molecule. So I need the simplest whole number ratio. Yes, exactly right. I'm going to multiply this whole thing by 2, which will give me a 2 to 7 ratio. That is the simplest whole number ratio, in which case the formula for the water of crystallization will be 2 zinc sulfate, 7 H2O. Okay, so please remember, when you're trying to find the simplest ratio and you divide by the smallest number and you get a 1 to 3.5 in this case, 1 to something and a half. You just multiply that entire ratio by 2, then you're going to get a 2 to 7 ratio. And this again will be the simplest whole number ratio in of the zinc sulfate to water. All right. Okay, now this also, yes, I see a hand. Please go ahead.
Sorry, so I just wanted to know if you have to always refer or like rewrite the formula. So if you just leave it in the ratio, that's wrong, hey?
Okay,
So
that would just depend on what they ask me. If they ask me calculate the value of X, then I would just say X is 7.
okay.
If they ask determine the formula, then I would rewrite it. Okay, so let your question guide you. Okay.
Okay, thanks. So because they said calculate the number of moles of water of crystallization. So where would you see that with your 7?
Yeah, so then I can stop there.
Okay.
Okay, but there is no harm in rewriting the formula. No harm in doing that, but that would be sufficient for your answer. All right.
Okay, thanks. So
Cool. Thanks for asking, Chris. Right. That kind of brings me now to empirical formula and molecular formula. IEB, you also need to be doing this. It's very much the same as the water of crystallization. It's all about the ratios. Okay. Empirical formula is going to be the simplest ratio, whereas the molecular formula is the actual ratio. So empirical, simplest ratio, molecular formula, actual ratio. Right. Okay, now usually when we want the empirical formula, I'm saying usually, we will give that to you in percentage. We'll say this substance consists of 40% sulfur, 60% oxygen. Okay. Ultimately, what we want to do before we can get ratio, we need to get it to mole, so we can go from mole to some sort of a simplified ratio. So that's what you have to keep in mind. We want to go from mole, which is number of particles, and we want to take that to a simplified ratio. Okay. Now, in order to get to mole, there's sometimes a bit of a process that we're going to have to go through. So if we have percentage, we'll take that percentage and convert that percentage to mass. Then we're going to convert from mass to mole, and we're simply going to do that with the M over capital M formula, mass divided by molar mass, right? And then, like I've shown you now, to get from mole to the simplest ratio, we just divide by the smallest ratio number. So usually if it's given in percentages, then we want to go from percentage to mass, from mass to mole, from mole to the simplest ratio. In other examples, like the one we'll be calculating a bit later, they don't do this part. They don't give you percentages. They just give you the mass straight away. Then I don't need to worry about the size of the sample. Then I can just go straight from mass to mole and mole to ratio. Ultimately, when you want empirical molecular formulas, this is the part that you need to be focusing on. Somehow I need to take whatever information I have, take that to mole of individual elements, so that I can get the ratio of individual elements. Now, if it's given as a percentage, then we would start by assuming that 100 grams of the compound is analyzed. Do we know for a fact that it will always be 100 grams? No, we don't. Okay. So if you want to punish yourself, assume that there's anything other than 100 grams, go ahead. Right. But the reason why we assume that it's 100 grams is that we can say if it's 40%, and we know that percentage is always by mass, then 40% of 100 grams will be 40 grams. And 60% of 100 grams will be 60 grams. Could there be a sample other than 100 grams? Of course there could, okay? But that's not the point here. If you want to assume 25 grams, you can do that, but then you need to work out 40% of 25 grams. That's a calculation. 60% of 25 grams. Okay, so to save yourself suffering, we assume 100 gram sample, which means we can convert percentage straight to mass. Okay. Again, it's an assumption. If I only had 25 grams, it really wouldn't matter because it would be the same substance, so it would have the same ratio of atoms in the molecules. I'll just have a smaller sample. Okay, so that's why we're allowed to make assumptions here. Once I've got mass, I'm going to convert that mass to mole, okay, like we would normally do. Only thing that you've got to be careful with here is this oxygen is now not, it's not diatomic, okay, it's not O2, because this oxygen is actually part of a compound. So this is actually sulfur of some number and oxygen of some other number. And because we don't really know what that number is yet, we're just going to divide by the molar mass of one oxygen. And we'll do the same for any compound where we have diatomic elements. We will not be using the diatomic nature of that substance. We will be dividing by the molar mass of one of those atoms. Okay, and then we'll find what that value is going to be at the end. Right, now once I've got my number of moles, then this is 1.25 and 3.75. So then I can actually just say, that was sulfur, right? So then I can say sulfur in ratio to oxygen is 1.25 to 3.75. Divide that by the smallest ratio number. And you don't really need to show this division. You just need to remember to do it. If I divide that by the smallest ratio number, I'm going to get 1.3. Okay, and you're allowed to round off here. So if this answer comes to 2.99, round it off. If this comes to 2.89, round it off. Okay, but if this answer was 1 to, let's say this was 1 to 1.5, that's halfway. So then we're going to say that means my ratio is a 2 to 3 ratio as the simplest ratio. Okay, but 2.99, 2.89, or 3.1 something, 3.2 something, round that to 3. Right, if it's around 0.5, so 0.5 or 1.49, then multiply it to get your whole numbers. All right. So we put it in a ratio and we simplify a ratio. I have to get to mole first so that I have number of particles, then I get the simplest ratio of those number of particles. If they are asking us to determine the empirical formula, then I'm just going to write out my formula in terms of those ratios that I've calculated. Now, if we need to go on to calculate, if we need to do this from mass, then we're basically just skipping this first step. Okay, we're just going to skip that first step. Now everything is already in mass. So we don't have to now convert by 100 grams first. So all we're going to do is we're going to take the mass that's given, convert that to mole, the mass that's given, convert that to mole, put the moles into a ratio. This would be 0.02 to 0.02, so it's a 1-to-1 ratio. And that 1-to-1 ratio tells me that magnesium oxide is simply MgO. Right. If we need to convert from empirical to molecular, we know that this empirical is the simplest ratio. So the molecular formula will always be a whole number multiple of this empirical. So let's say the empirical formula is CH, let's say it's CH2. That means, so this would be empirical. That means that the molecular could be C2H4, C3H6, C4H8, etc., etc. So if I want to convert from empirical to molecular, I need to bear in mind that each one of these conversions, I am simply multiplying by some factor, multiplying by 2 or 3 or 4. So the whole point of calculating the molecular formula is I've got to figure out what is this ratio. Okay, now to do that, we need to look at the masses that are given, or the molar masses that are given. So if we know that the empirical formula is, say, CH2, then I need to go and determine what is the molar mass of that empirical formula. So that's 14. But I know that the molar mass of the actual substance is 56. So if I divide that, then I get a ratio number of 4. And that ratio number of 4, I am then going to multiply back into my equation. Okay, so I need to get from empirical to molecular. I need to have the empirical first, and then I need to identify or figure out what is that conversion ratio. To get my conversion ratio, I'm going to divide the molecular formula mass, which will be the larger of the two. I'll divide that by the empirical formula mass, which is the smaller of the two. All right, Grace, let's have a quick look again. Step 1 and 2. Step 1, determine the empirical formula. I need to have the empirical formula already. In this case, it was given. If it's not given, then I can use what we've done over here. Okay, percentage to mass, mass to mole, mole to ratio, or mass to mole to ratio. But the point is that step 1 would be to get the empirical formula. Once I have that empirical formula, then I'm going to calculate what is the molar mass of that empirical formula. So if the empirical formula is CH2, that's going to be the mass of carbon plus hydrogen plus hydrogen. That will tell me what is the molar mass of the empirical formula. So what is the molar mass of the simplest ratio? Now this 56 is the molar mass of the actual ratio. So if I take this 56 and I divide this by 14, then I'm going to get a conversion factor of 4. Okay. This conversion factor of 4, I'm going to multiply back into my empirical formula. So it will be 4 times 1 carbon gives me 4 carbons, or 4 times 2 hydrogens will give me 8 hydrogens. And then I've calculated the molecular formula. All right. Now I'm going to do another one with you, and you're going to work through this one with me. It is in your question pack. I'm going to just have to quickly scroll to get those questions back again. So it's section 3. Okay, section 3, it's question 3.3. That's the one that we're going to be looking at now. Okay, it's an empirical formula question. It's a little bit more complicated. So please follow along. All right. I'm just going to go back to the previous slide for the sake of somebody that wants to write something down. Okay, while they're copying this down, any questions? Something that you'd like me to clarify at this point? Maybe there will be something that comes up as we do the questions. So please let me know. Yes.
So were you given your molecular formula mass, or will we ever be given the molecular formula mass in a exam or something like that?
Okay, if I want to determine this molecular formula, if I want to determine this, then they'll have to give me the molecular mass of that compound. They will have to give it, okay, always, for the actual compound. There's no way to do this conversion without them giving me the actual molecular mass, because that actual molecular mass will tell me what the ratio is. Okay, so they will have to give that value to me. Otherwise, there's no way that we can do this calculation. All right. Rutendo, you can let me know if you're done with this, then I can move on. All right. So we are looking at question 3.3. So here they say, in order to determine the empirical and molecular formula of a compound, CXHY, a certain mass of the compound is burnt completely in excess oxygen to produce 74.1 grams of carbon dioxide and 19.35 grams of water. Okay. The first question that we're going to tackle is this number 2. Use relevant calculations to determine the empirical formula of the compound. So let's start by just writing out this equation. CXHY plus O2, because they said it's burnt completely in excess oxygen. So it's reacting with oxygen. This produces carbon dioxide and water as the only products. And then they gave us the masses there for the carbon dioxide was 47.1 grams. And they gave us the mass of the water, 19.35 grams. Okay, and now they want to know what is the empirical formula. So in other words, this substance, what is the formula of that substance actually, the simplest ratio? All right, now first thing that we need to note here is that this carbon and hydrogen, which was together, has now been separated. And the separation of this carbon and hydrogen now landed up in the carbon dioxide and the water. Now, ultimately, if we want to know what the empirical formula is, I said to you, we need to get moles of our elements, and we need to convert that then to a simple ratio. Okay, or simplest ratio. So this is what we need to be focusing on in terms of the solution. We need to figure out, how am I going to get the number of moles of elements? Now, first off, these values that are given are all masses. So let's start and we just convert those masses to mole. So now I'm going to write a number of mole, and in brackets, I'm going to put CO2, okay, so that I know I'm busy working with carbon dioxide, and that's mass divided by molar mass. So this is going to be 47.1 divided by carbon, which is 12 plus 16 plus 16, so that's divided by 44. Okay, and that's going to give me 1.07 mole. Okay, then I'm going to do the same for the water. Number of moles of water is equal to mass divided by the molar mass. So that's 19.35 divided by 18. 19.35 divided by 18 is 1.08 mole. Okay, so now what I've done is I've just taken those masses and I've converted them to moles. Okay, because I want to be working in moles all the time. So if you're really not sure, oh, where do I even begin? Do a conversion. Get everything to mole first. Okay. Ultimately, I'm looking for the mole of the elements. And the elements that I'm dealing with here is carbon and hydrogen. So I need to go and I need to go take this carbon and hydrogen out of this value here. This 1.07 mole, that is for CO2. And the 1.08, that's for H2O. I need the moles of each individual element. Okay, so what I'm going to do for the CO2 is I'm going to say carbon dioxide in ratio to carbon. So if I have one carbon dioxide, I will only have one carbon. Look, there's a 1 there. Okay. So that means if I have 1.07 moles of CO2, I actually have 1.07 mole of carbon. Okay, so now I have the number of moles of my first element. We can do the same for the water. Okay, but now if I look at the ratio of water to hydrogen, then one water molecule is going to produce 2 hydrogen atoms. There's 2 hydrogen atoms in each water molecule. So one water contains 2 hydrogen. So that means 1.08 moles of water will contain 2.16 mole of hydrogen. Once again, I now have number of moles of the element. Okay, last step is to get that simplified into a ratio. So carbon to hydrogen is a 1.07 to 2.16. Divide by my smallest ratio number, which is the 1.07, and this will give me, let's see, 2.16. I want to do that exactly. So this will give me 1. This will give me a 1 to 2.018, blah, 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 blah. But that I can round off to 1.2. Okay, and the reason why I'm rounding off is because I want the simplest whole number ratio. Okay, let's have a look. Apparently, you're not happy with what I did with the water. You want water to be a 2-to-1 ratio. Okay, have a look here, guys. If I have one water molecule, so for every one water molecule, if I break that up, there will be 2 hydrogen atoms. Okay, one molecule of water will give me 2 molecules of hydrogen. So maybe I can write it out like this. Maybe this will help you a bit. If I take the hydrogen and I take it apart, that would be hydrogen and oxygen. And to balance this, I will form 2 hydrogens and 1 oxygen. So that means that the water and the hydrogen is in a 1 to 2 ratio. Okay. I know it looks confusing because there you see 2 hydrogens, but I wrote 1, and there you see 1 hydrogen, but I wrote 2. Okay, but think about it in terms of this process. Maybe if you write it out for yourself like that, it will help you a bit. One molecule breaks up to form 2 water. One water molecule breaks up to form 2 hydrogens. So it's a 1 to 2. Okay, I hope that's clear. Okay, cool, awesome. All right, you need to be doing the same thing for your ions, by the way. So I think this is a good teachable moment. So same for ions. So let's say I have aluminium, let's say I have aluminium oxide. And now I want to know how much aluminium is there. Then I'm going to say, right, if I break this up into aluminium and oxygen, there will be two aluminium, and there will be 3 oxygen. So aluminium oxide to aluminium will be a 1 to 2 ratio, or in ratio to oxygen, it will be a 3 ratio. Okay, so think about it in terms of splitting it up, and maybe write it out if it's going to help. All right, cool. So now we got that. We've got the ratio, and the question said write the empirical formula. So that then I'm going to do that. C, there's 1 of them, and then H, there are 2. Okay. Ladies and gents, if you look at this question at face value, you see C, X, H, Y, and masses of products. It looks overwhelming. It looks like it's going to be complicated. All right. But remember the basic principle of empirical formulas. We want the moles of the elements to put it into a ratio. That's what we want, okay? Whether that's from a percentage or whether that's from a reaction, doesn't matter. I'm going to look for the mole of the element and the mole of the element. Yes, I might go find it over here by converting that to mole and finding out how much carbon is there, converting that to mole and finding out how much hydrogen is there. But it's a chemical equation. So the carbon and the hydrogen that exists on the left will still exist on the right. Can't disappear. Okay, so if I calculate the moles of carbon in the products, that will tell me the moles of carbon in the reactants. The moles of hydrogen in the products tells me the mole of hydrogen in the reactants. Okay, this conservation of matter. Right. So ultimately, look for the mole of the elements and then simplify that. Right. So if you get masses, just convert it to moles, and then you're halfway there. Rightio, now we can move on to the value to question 3. Okay, so my empirical formula was CH2. Now they're saying the molar mass of compound is 28 grams per mole, determined by using calculations the value of X and the value of Y. So what is the actual value of those? Now that value is not 1 and 2. Okay, 1 and 2 is the simplest ratio of that values. With the CO2, sorry, before we go on, I just want to make sure that we cover everybody's questions here. With the CO2 and C ratio, is it 1-to-1 because they are both diatomic molecules? Kiabetsi, let me just explain it to you like this, and I'm hoping that this is going to answer your question. If I take CO2 and I break that up completely, it's going to form carbon and oxygen, okay? There's going to be 1 carbon formed and 2 oxygens. Now, it doesn't really matter if you want to write the oxygen like that or like this. At this point, I'm just looking at the ratios. So 1 carbon dioxide will form 1 carbon, and that's a 1-to-1 ratio. Okay, cool. Right. All right, so this empirical formula that I've got here is the simplest ratio. So this X and Y in CXHY, that could be 1 and 2, or it could be 2 and 4, or 3 and 6, or 4 and 8, or 5 and 10. Okay, it could be 20 and 40, as long as it's a 1-to-2 ratio. So what we're doing now is we're calculating the actual values of X and Y. So we are calculating the molecular formula. Now you'll notice that they have given us here the molar mass of this compound. So we're going to start by first getting this mass. So the molar mass of my empirical formula, molar mass of CH2 is 12 plus 1 plus 1, and that's 14 grams per mole. Then I'm going to take the actual molar mass divided by that value, and that's going to give me my ratio. My ratio in this case is a 2. So therefore, this CH2 becomes C2H4. Now the question did not ask for the molecular formula, but rather asked for the values of X and Y. So I would prefer to then see X is equal to 2 and Y is equal to 4. Okay, try and answer the question as directly as you can. If they say calculate the values of X and Y, show us X is 2, Y is 4. Okay. Cool. Okay, so that was just a nice example for you to see empirical and molecular formula asked in a slightly different way. Okay, asked from a different angle. Is there anything that you want me to clarify on this empirical formula, molecular formula, and the example that we've just done? Is there anything that you want me to clarify? Please ask now. I know I'm going at quite a rate because I want to do lots of example questions after the break. Okay. Well, if there's no questions, then we're going to take a break. Jump back to question 3.1. All right, and we're going to quickly talk about the concept of limiting reactants. Now, in this question that I'm going to use as my example, they say there's 15 grams of ammonia and 25 grams of oxygen present. So they're telling us that there's a very specific amount of the reactants present. Okay. Now we're going to do some calculations based on these two reactants. Now, it's important to note that the thing that will determine this entire reaction is the reactant that will run out first. Let me give you a practical example. You're going to make a cheese sandwich. Slice of bread, cheese, slice of bread. Nice and simple. Okay. Depending on whether you've got more cheese or more bread, that will be the limiting factor. So it doesn't matter if you've got 40 loaves of bread, but you only have 3 slices of cheese. Once you've used up your 3 slices of cheese, ain't no more making a sandwich. Okay. So those 3 slices of cheese will say that that's the limiting reactant. Those 3 slices of cheese will run out because no more sandwiches can be made. Those 3 slices of cheese would have determined how much bread we used. Those 3 slices of cheese would have determined how much sandwiches we were able to make. So whenever we have a specific amount of 2 substances, we need to figure out which one of those are going to run out first, because that's going to determine how much reactants I use, how much products I'm going to form. And this is what this question is all about. So the first part of the question is something that you would normally go through. They might ask it explicitly, they might not. But the first part of the question is to calculate the number of moles that are present. So we're going to start with the ammonia. We're going to say the number of, oopsie, that's not even close, lowercase, number of moles of ammonia, NH3, is equal to mass divided by the molar mass. So that's 15 divided by 17. Okay, and I hope you're doing this with me on your calculator. You're faster than me, please pop the answers in the chat, and I don't have to wonder whether I'm correct. Okay, so I have exactly 0.88 moles of ammonia. I can also calculate my number of moles of oxygen. And now notice that they have indicated this is diatomic oxygen. So when I do my calculation of mass divided by molar mass, I'm going to be doing 25 divided by 32. Now that's 2 times. Cool. Thanks, Priyanka. That's 0.78 moles. Okay, can somebody please confirm that answer? Pop it in the chat. Let's see if she's right so we can move forward. Cool. Thanks, Bonatti. Right. I've answered the question. The question says calculate the moles of reactants present. Now the next question says determine the limiting reagent. So now I know that these are the 2 things that I've got. I've got so much ammonia, so much oxygen. Now I've got to figure out which one's going to run out first. I'm going to show you a method that I always recommend to my kids, and I find it works well. Okay. We first start by putting these 2 things that are going to react into a ratio. The ratio numbers we're going to find from the balanced equation. So this is a 4:5 ratio. Then I'm going to pick one of those 2 substances. It really doesn't matter which one you pick, just pick one of them. So I'm going to pick ammonia because it's first. So I'm going to say here, ammonia, there's 0.88 moles of ammonia, and I'm going to underline this to remind myself that that's the amount that I actually have. Then I'm going to calculate this value over here. Now, in order to do that, just in case you're not so comfortable with ratios, you divide by 4, and you multiply by 5. I remember that by saying I break up, okay, divide, so I break up, and then I times across. So I break up and times across. Times is across. Okay, hope that helps you to remember. So 0.88 divided by 4 times by 5, that's going to give me 1.1 mole. Okay, so what this tells me is that if I use all of my ammonia, I would need 0.10 mole of oxygen. So now I'm going to write it out for my reasoning. I'm going to say 1.10 mole of O2 is needed, but we've already calculated that only 0.78 mole O2 is available. So now I can see that I actually have less than what I need. So therefore, this oxygen is going to run out first, and oxygen is my limiting reactant. Okay. So I calculated how much am I going to need. I said I only have 0.78. I've got less than what I need. So that means it's going to run out. Let me show you the other way around. If I decided not to work with the ammonia, but with the oxygen instead, I would have still started with this. Ammonia to oxygen is a 4:5 ratio. And then I would have said, okay, oxygen, 0.78 mole. That's how much I have. Okay, let's figure out how much am I going to need. Divide by 5 and times by 4. Thank you. I agree with your answer there. So that's 0.624. Okay, you can round that to 0.62 if you want. Now let's check our story. So our story says 0.624 mole of NH3 is needed. But I calculated over there that 0.88 mole of NH3 is available. So if I look at my ammonia now, I have more than what I need. So therefore my ammonia is in excess. I have more than what I need, and that would make my oxygen the limiting reactant. Okay, so you can do it either way around. Doesn't matter which one you pick. Do both if you want to be sure. Just take one of them, use up all the ammonia, figure out how much oxygen you need, or use up all the oxygen, figure out how much ammonia you need, and based then on how much do I need, how much do I have, you'll be able to see which one is going to run out first. Okay, so that's generally the method that I recommend. Do it once, don't have to do it twice. If you want to, you can, just to be sure, and it doesn't matter which one of those two you pick. What is important now is that I have determined that the oxygen is the limiting reactant. So what I'm going to do on my question paper is I'm going to highlight or circle the oxygen. And I'm going to write there limiting. Because the oxygen is now my slice of cheese, the oxygen is going to be the thing that will determine everything else about that reaction. So if I look at question C, I just want to write down the value here. That was 0.78 moles. Okay, so that I can clear this one. Oh, not that much. Let's try again. Here we go. Okay, so if I look at question C, it says how many molecules of water will be formed? The amount of water formed is dependent on my limiting reactant. So I'm going to start by saying oxygen in ratio to water. And this is now a 5:6 ratio. I have 0.78 moles of oxygen. What am I going to write for the water? So it's 0.78 divide by 5 times by 6. Okay, I like it. Thank you very much. Right. If you want to stick to 3 decimal places, perfectly fine. If you want to round to 2, that's sufficient. Not less than 2. Okay. 0.94 moles. So now that I know how many moles of water I've got, remember the question now ever asked for how many molecules. So they want to know how many individual particles are there. Now I'm just going to have to use Avogadro's constant. 0.94 is equal to the number of particles divided by Avogadro's constant, 10 to the 23. So my number of particles is going to be, see, 0.02 times 10 to the 23 multiplied by 0.94. That should be 5.66 times 10 to the power 23. And the unit here is going to be molecules. Okay, so I've used ratio. That's what reaction's all about. It's all about ratios. Okay, and then I just need to make sure that I convert from the ratio or the value that I got back to the asked quantity. They asked for the number of particles, so I'm going to do that with Avogadro's constant. So notice that to get the amount of water, I use the limiting reactant with water. For the next question, what is the volume of NO formed, nitrogen monoxide formed at STP? Now I'm going to do oxygen in ratio to nitrogen monoxide. Okay, again, limiting reactant in ratio to my product. This is a 5:4 ratio, so 0.78. Okay, let's see the answers come in there. See what you get. Yes, Benati, happy with that. Takatso, good. Let's see if we can get one more. Yes, Tapong, happy. 0.62 mole. Good. Rotendo, happy with that. All right. Again, if you want to do more decimal places, you're welcome. Remember that the question asked for volume, and this is now volume of a gas at STP. So I can say number of mole is volume divided by the molar volume, where the molar volume in this case will be 22.4. Okay, let's see those answers. See what you get. So Katso, just check your rounding there. Amara, Chris, check your rounding, please. Okay, I suppose it will depend on whether you've used 0.624 or just 0.62. If you use 0.62, you'll get 13,888, which rounds to 13,89. And the unit will be in cubic decimeters. All right. Okay. All right. Now, that was a little bit of a warm-up. Now we're going to write. For percentages, there are 2 percentage questions that you're going to get. Percentage purity or percentage yield. Okay. Just to help you out, because how do I approach this? Percentage purity, we always start with the products and we work back to our reactant. And that would be the impure reactant that we're working towards. Okay. The reason why we do that is because in any chemical reaction, it's only the pure component that will react. So if I look at my amount of product and I work that back to reactant, then I know how much actual reactant reacted. Okay. So if I look at the amount of product I formed, then I know of my impure sample, how much was the actual reactant. And based on that, we can then go and do a calculation. Remember that this percentage of purity is usually by mass. Okay, so we need to make sure that we're converting to mass to get percentage purity. Okay, mass, critical, must be mass. So I take my product, I work back to the reactant, see what was the actual mass of reactant used, and that would be the pure part of it. Divide that by the total amount that I had, and then I'll multiply that by 100 to get the percentage. Okay, we'll look at an example of that in a moment. Okay, the other percentage question that you're going to get is yield. For yield, I am going to start with the reactant, and I'm going to work towards product. Okay, because the percentage yield means how much I get out of it. So I'm going to have to go look at how much did I get out of this reaction, and I'm going to compare that. Remember, percentage is just a comparison. Okay, if I say it's 80%, it means I got 80 parts out of 100 that I would have got. So I'm comparing it to what I potentially could have got. Okay. If you say that you got 99% for science, that means that's a comparison. You're comparing your actual mark to what your total was. All right. So I'm going to get my reactants, and I'm going to work towards products so I can figure out how much product could I have made. Okay. So I'm going to calculate my potential product. So how much could I make? And then I'm going to divide what I actually got. So the mass that was produced, I'm going to divide that by the theoretical mass. So how much did I get out of it in comparison to what I could have got? Okay. So that's how we're going to handle percentages. For purity, we start at the back. We start at the products. We work to the reactants. For yield, we start at the reactants and we work towards the products. Right. In terms of the yield, here it says mass, but please remember that you can also do yield in terms of number of moles of the actual product. Okay, divided by number of moles of theoretical product. Because this potential product that you're forming is going to be a pure substance, it means that you can do the conversion or the comparison in terms of mole as well. You can also do it in terms of volume if it's a gas, right? You can only do that for yield. You can't do that for purity. Purity must be by mass. So if you're worried that you're going to forget, stick to mass. Okay. So let's have a look at that in terms of this the context of this question that we've already warmed up on. So it says if 4 grams of water forms through this experiment. So that is actual. That's how much I actually got. Now they want to know what is the percentage yield for this reaction. Okay. So they want to know that 4 grams that I made, what does that represent in comparison to what I could have got? Okay. Remember, for yield, we start from reactant, we work towards product. So the reactant that we're going to use will still be our limiting reactant. And we're going to put that in ratio with this potential product, which will be water. And we worked this one out before. This is a 5:6 ratio, 0.78. And now I can't remember what it was. 0.78 divided by 5 times by 6. So that's 0.94. 0.94 moles. Okay, so that's how much water I could have made. Theoretically, used up all of my oxygen, that's the amount of water I could have made. Now I can convert that to mass, okay, because this was given in mass, so I want to make sure that my units of comparison is the same. Convert that to mass, so mass divided by molar mass, 0.94 is equal to mass divided by 18, so the mass is 0.94 times 18, so that is 16,92 grams. Right, so that now tells me that if I use up all of my oxygen, I could potentially get 16.92 grams, but now we know that we actually got 4 grams. So to get my percentage yield, I only managed to make 4 of this potential 16.92 grams. I'm going to multiply that by 100 to express it as a percentage, and that's going to give me 23.64%. Okay, so you can see this is a very low yield. Okay, this is not a lot, not a very efficient reaction. You didn't get as much products as you potentially could have gotten out of this reaction. Now, why is it so little? Okay, where's the rest of that stuff? We just maybe did not convert all of the reactants into products. Remember, the water molecules can't just disappear. So if I only manage to make 4 grams, it means all the other stuff is still in reactant form. There's still some oxygen and ammonia particles floating around in the container and have not reacted yet. They're gases. Gases are far apart, so it's potentially possible that they could not have collided yet, but they're still there. Okay, so anything that's not converted, this my maths is failing me now, but that's 76.36%. That part that I didn't get, the 76.36%, that is just things that have not reacted to form products yet. Okay, and that's the answer then for F. Give a possible reason why the actual yield of water is less than theoretical yield. Not all of the reactants have reacted. Okay, not everything has changed. Not all of the oxygen is converted. Okay, so that is a potential reason. Another potential reason we see mostly if it's a solid as a reactant, these were all gases. But if we see solids as reactants, one of the potential reasons could be there's impurities in my substance. So maybe this 15 grams of ammonia that I thought was ammonia wasn't all ammonia. There was ammonia and some other stuff in there. Now the ammonia is going to react, the other stuff won't. So it's also possible that there might be some impurities present in my reactants. All righty then, let's go to another one of these percentage-based questions. That was, I think, question 2. Sorry, I just want to make sure that I get the right question here. Yeah, question 3.4. Right, question 3.4. Okay. They say ozone reacts with nitrogen monoxide gas to produce nitrogen dioxide and oxygen. The nitrogen monoxide gas forms as a result of emission from motor vehicles and jet planes. First question is, give a balanced equation between O3 and NO. Now here they said O3 reacts with NO. So I'm going to write O3 plus NO to produce NO2 and oxygen. So that's NO2 plus oxygen gas. That's now on its own. So it must be diatomic. Okay. Then we need to make sure that this is balanced. There are 4 oxygens on the left, 3 and 1. So 4 on the left and 4 on the right. There's 1 nitrogen, 1 nitrogen. My equation is balanced. Happy. All right. Now we get to the next part of the question, which says, in one such situation, 74 grams of O3 reacts with 67 grams of nitrogen monoxide. And that's when you start seeing those red flags, specific amount, something's going to run out. Okay, we know we're going to need to be figuring out limiting reactants here. So the first part here says, calculate the number of moles of O3 and NO present at the start of the reaction. So I'm going to give you, okay, so you would have had to calculate the number of mole that you have present in the beginning. Easy 5 marks, right? You got 1.54 moles and 2.23 moles of those substances respectively. just notice the format notation that I'm using here. Okay, there's nothing wrong if you leave out this piece. If you leave that out, it's not wrong. But given the fact that I'm going to be working with these values again, it's just making my life a bit easier if I label. Because if I just have n is m over m, n is m over m, n is m over m, I'm going to get confused. And I'm not going to know which value that I work out where and take time, figure it out again. Let's not do that to ourselves. All right, now next question says, identify the limiting reactant in the reaction and justify your answer. Now, given that this O3 and NO is in a 1-to-1 ratio, it's very easy to see that the the ozone is going to be the limiting reactant. Okay, but I will still, just to justify my answer, I will still show this process. So I'll put 1.54 there, and I'll put 1.54 here. Underline that because that's what I've got. And then I'll say 1.54. If I use all my ozone, if I use all of the stuff I've got, then 1.54 moles of NO is needed. 2.23 mole NO available. So for the nitrogen monoxide is in excess. So therefore ozone is limiting. Okay. Remember, you could also do it the other way around. But now I'm going to go back and I'm going to go on my question paper and I'm going to go highlight that ozone because that's my limiting reactant. I want to remember that I've got to be using that every single time. Okay. Now we can get rid of this. So the ozone was 1.54. Okay. All right, next question says, calculate the mass of NO2 produced. So we know that we're then going to have to use our limiting reactant in ratio to NO2. And this is a 1-to-1 ratio. So, and I forgot what that value was. Okay, please help me out with this value, please, somebody. What did we just calculate that to be? 1.54, thanks. 1.54 moles, and that will form 1.54 moles. Okay, remember the ozone was my limiting reactant. Okay, now I've got the number of moles. Last step, convert that. Chris.
Sorry, so this might be a dumb question, but I'm just confused as to how you got a 1-to-1 ratio with your sodium oxide and your ozone in the previous, or the nitrogen monoxide, sorry. Not
the nitrogen monoxide and the ozone.
Yeah, when it was O3 to NO.
I just looked at these balancing numbers here.
Oh, okay.
So that's a 1 and that's a 1.
Okay, thanks. I appreciate it. Thanks.
Okay, cool, no worries. Okay, so we got that. This is then going to be 1.54 is equal to mass over 14 plus 16 plus 16, so that's 46. And Benotti, I'm going to take your word for this one. That looks like a good answer. 70.84 grams. Okay, there's our product. All right. Remember, figure out which one runs out. Use the one that runs out to figure out how much product you can make. Limiting reactant determines the amount of products. All right, now we're going to get to a purity question here. Let me just take all of this away. We've got a new situation now with some acid and impure iron, and there's going to be some hydrogen gas being liberated here. Okay. says dilute sulfuric acid reacts with 20 grams of impure iron. Impure means that if I take this total 20-gram sample, there will be some of that would be iron, and there would be some other stuff. Let me use a different color because that's so wrong. There will be some other stuff that will be my impurity. Okay. So the 20 grams, I cannot say that's 20 grams of iron. Iron makes a part of that 20 grams, and I don't know how big that part is. So now we get to the question where it says, oh, and they say 5.6 cubic decimeters of hydrogen gas is liberated at STP. Okay, question 2. Calculate the percentage purity of iron used above. So what they're saying is, we know there was 20 grams, but what part of that was actually iron? Now remember, if I want purity, I work from products back to reactants. So the only product that they gave me information for was this hydrogen gas, okay? And they gave me hydrogen gas in terms of volume at STP. So I can say number of moles of hydrogen gas is equal to volume divided by the molar volume. So that's going to be 5.6 divided by 22.4. Okay, and I need the confirmation because this answer looks too good to be true. Such a clean answer. 0.25 mole. Thanks, Mamelo and Bonatti. 0.25 mole. Okay, so now I've got the product. Now I'm going to work from product back to reactant. So I'm going to put the product and the reactant that I'm trying to determine, the iron, I'm going to put those into ratio. But just to make sure that they're not pulling a fast one on me, I want to make sure that this is actually balanced. So that's H2 and H2, SO4 and SO4, iron and iron. Okay, so that's all balanced. They did say it was balanced, but just wanted to make sure. All right. So now I'm going to work from products, which was the hydrogen. Let's just go over here. Hydrogen in ratio to the iron. Okay, products back to the reactant that I'm trying to determine. And in this reaction, we can see there's a 1 and a 1 ratio. So this is a 1-to-1 ratio. The hydrogen was 0.25. So that would be 0.25 moles. Okay, now remember, if we do purity as a percentage, I want it to be in mass. So number of moles of iron will be mass divided by molar mass. 0.25 is equal to mass divided by 56, I think. Let's just double check. Yep, that's 56. Right, so 56 divided by 4 will be Takatsu and Rutendo, I agree, 14 grams. Okay, so now we know that of that 20 grams, 14 grams was actually iron. So 14 out of the 20, express that as a percentage. So 14 out of 20, that's 70% purity. Okay. Cool. So I hope you can see that approach. If I want purity, start over the products, work back to reactants. Okay. I'm looking for iron. So I'm going to work from the total products that I made back to iron. The only product that was given was hydrogen. So I'm going to go back with hydrogen back to iron. Right, in a certain industrial plant, 3,610 kilograms of titanium chloride is reacted with magnesium to produce titanium. Watch out for this. It's now given in kilograms. It needs to be in grams. So this is going to be 3610000 grams, 3,610,000 grams. Okay, from kilograms to grams, I multiply by 1,000. So I must make sure that that is in grams. And the same thing is going to happen here when I do the products. Okay, so let's first start with the first question, which says calculate the amount of titanium produced. Now, if we look at the question, it says that 3,610 grams of titanium chloride is reacted with magnesium to produce titanium. They didn't tell me how much magnesium there is, so then I can assume that the magnesium is in excess. We can assume there's more than enough magnesium. If they only give me one amount, that was wrong. If they only give me one amount, then I can assume that that one amount is the limiting reactant. Okay, so if we want to know the amount of titanium produced, we're first going to start by calculating the number of mole of that limiting reactant. The titanium chloride is mass divided by molar mass. 3610000 divided by, I'm going to have to work this one out quickly. So titanium. So now remember, I'm just getting these values off of my data sheet. Okay, so titanium is 48 plus 4 chlorines, and chlorine is 35.5 each. Okay. Okay, Rutendo and Kahatso, thank you for your answers. I agree with those. Who else answered? Yeah, let's have a quick look. Kahatso, you fixed it. I'm happy with that. Okay. 19,000 mole. Nice big answer. So that's my limiting reactant in terms of mole. Okay. I didn't have to determine the limiting reactant, but I'm still going to consider this my limiting reactant because that's the one that they gave me a specific amount for. So if I want to know the amount that I can make, then I'm going to put the limiting reactant in ratio to the product that I'm trying to determine. This is a 1-to-1 ratio. Again, looking at these numbers in my balanced equation is a 1-to-1 ratio. So 19,000 mole will produce 19,000 mole. They asked for the amount, so I can leave that in mole. Okay, no problem with that. Right. Okay, then the last part to this question, C, calculate the percentage yield of the titanium if only 980 kilograms was formed. So if I want to know what the yield is, I now know the amount that I actually got, but I need to figure out how much could I potentially have made. The amount that I potentially could have made was 19,000 moles. So I just need to convert that into mass. So the number of moles of titanium is mass over molar mass. This is 19,000 is equal to mass divided by 48. So 19,000 times 48. This is a good, thank you very much. 912,000. And remember, this is in grams. So I can now either do one of two things. I can either leave it in grams, or I can say this is 912 kilograms. I just need to do the comparison based on mass, and I can do that either in grams or kilograms. Okay, but it will still be in terms of mass. So I made 980 of the potential 912. Sorry, 890 of the potential 912. And times that by 100, that gives me 97.59. Is that right? Did I do that right? Yeah. 59%. Okay, nice, very, very big yield. Good amount of substance made compared to what I could have got. All right, I just want to quickly go back into the chat. I see I missed a question somewhere. How did we know that titanium was the limiting reagent? I'm assuming that you're talking about the titanium chloride, okay? So I knew that the titanium chloride was the limiting reagent because they gave me a specific amount of titanium chloride, and then they just said it reacts with magnesium. So because I have a specific amount of titanium chloride and no given indication about the amount of magnesium, then I can assume that there was more than enough magnesium. Okay, because they said that this amount of titanium chloride reacted with magnesium. If they gave me a specific amount of titanium chloride and a specific amount of magnesium, then I would have to figure it out. Okay, so I hope that answers your question, Chris. If I have one, cool. If I have one given amount, that must be the limiting reagent. Righty. I think we've got time for one more question. So let's see if we can tackle this. Yeah, let's tackle question 3.5. Okay, because we love graphs, right? We love seeing graphs and questions. It just warms our hearts. Question 3.5. A learner adds excess hydrochloric acid solution to calcium carbonate grains. Look at what they're saying here. Excess of hydrochloric acid solution. So immediately I'm going to go to calcium carbonate and I'm going to highlight that. Okay, because if the HCl is in excess, the calcium carbonate must be the limiting reagent. I hope that's clear. Excess hydrochloric, that means calcium carbonate is going to run out. The concentration of the hydrochloric acid is then given there, 1.0, and the volume is 500 cubic centimeters. The reaction takes place, is represented. Then they give us some information here about the CO2 that's released. So the gas that's coming off, they're now capturing that in a nice big gas syringe, and they're measuring the volume over time. So what we can see here on this graph is that as this reaction proceeds, the rate at which the gas is formed is decreasing, and then at time 100 seconds, the amount of gas from that point on stays the same. So in other words, no more products are being formed. The reaction came to a completion. So the reaction at this point, 120 seconds, the reaction has run to completion. So the question that says, how long did it take the reaction to be completed? 120. Check your units. That unit says seconds, so I'm going to put seconds there as well. Okay, remember it could be minutes as well, so check your units. Right, determine the volume of CO2 gas that is formed. Now, determine, but it's 1 mark, so I can actually just go and read it off of there. So on my graph there, it's between 200 and 300. So that's going to be 250. Again, check your unit. This is cubic centimeters. Next question, which substance is the limiting reagent? Normally, you think, okay, I'm going to do a calculation comparison. But remember, it's a 1 mark question. And it's based on the fact that they already told us HCl is in excess. And they're just checking whether you read your question properly. So that means the limiting reagent will be calcium carbonate. Okay. Now, next question says, calculate the mass of calcium carbonate used in the experiment. The CO2 gas in the syringe is at a temperature of 25 degrees Celsius and is at standard pressure. Look very carefully at this question. The word standard there, STP, you just want to go and say V over VM, and VM being 22.4. That's what you want to do. Let me quickly take you to your exam, to your what you might call it, thingamajig, to your formula sheet. Okay, let me go show you something here. Here it says standard temperature is 273 Kelvin, and that is equal to 0 degrees Celsius. So this means that this substance is not at STP. Yes, it's standard pressure, but it's not standard temperature. Okay, so please make a very clear mental note of this. The memo for this section is not right. Okay, the memo in your notes is not right because they are dividing by 22.4, but it's very clear that this 25 degrees Celsius is not standard temperature. Okay, so I hope that's going to scream at you when you see this in the exam. Now, if they said you at a temperature of 0 degrees Celsius, that's fine. Then I could do that. Okay, but they've given me a different temperature. I cannot use 22.5. Okay, so now let's see. If I want to calculate the mass of the reactant, the only information they gave me here is the product that I've used there. Okay, I can't put the acid into ratio with calcium carbonate, the 0.1 and 500. I can't put that into ratio with the calcium carbonate because the hydrochloric acid was in excess. This 0.1 mole of 500 cubic centimeters was too much. Okay, that's like saying, how much cheese did I have? But I had 70,000 loaves of bread. Okay, I can't just use the 70,000. I have to go look at the fact that I only made 3 sandwiches. So I'm going to have to go look at the amount of product that I made, okay, because that's the specific amount. Okay, but now that specific amount, which is a gas, I cannot convert that just by 22.4. So because it's not at STP, I'm going to have to use my gas laws. PV is equal to nRT. Now, if you're in the IEB and you've never seen this before, don't have a panic attack. Okay. Pressure, standard pressure. They told us it's standard pressure, so we can go here. We can go find standard pressure. And remember, pressure must be, for this formula, must be in pascals. So that's 1,013 times 10 to the power of 5. 1,013 times 10 to the power of 5. Okay. The volume of gas that was produced. Now, for this gas law, volume must be in cubic meters. To go from cubic centimeters to cubic meters, we divide, or let's rather, we divide by 1,000, and then again divide by 1,000. Okay, because that's going to be cubic centimeters to cubic decimeters is divide by 1,000. And then to do that again to cubic meters, that's divide by another 1,000. All right. So the alternative that you can do there is you can say times 10 to the power -6. That's the same as dividing by 1,000 twice. All right. But this volume is 250 cubic centimeters. So that's going to be times 10 to the power -6 to get it to cubic meters. That's equal to number of moles, which is what I'm trying to calculate, multiplied by R, which is my gas constant, and the gas constant over there, 8.31. Okay, so times 8.31 times the temperature, which must be in Kelvin, so that's going to be the degrees Celsius temperature plus 273. Okay. So now I just need to solve for n. And that's a little bit of mathematics. So let's quickly get that. Number 103, 250 times 10 to the -6 over and 25 plus 273. Okay, so that gives us 0,01 mole. Okay. Rutendo, which part do you need me to re-explain? I'll happily explain it again. Just let me know where did I lose you? Standard temperature being 0. Okay, so on your formula sheet there, okay, we see there it says standard temperature is 273 Kelvin. Now 273 Kelvin is equal to 0 degrees Celsius. So how I know that is because to get my Kelvin temperature, Kelvin is degrees Celsius plus, okay, this is fucking. Okay, plus 273. Kelvin is always degrees Celsius plus 273. So if my Kelvin is 273, that means degrees Celsius must be 0. I think I just had load shedding. Can anybody please confirm whether they can still hear me?
So I can still hear you.
Yeah, you're still good.
Cool, thank you guys. I just lost my second screen, so give me a second just to get my. It's non-standard conditions, so therefore then I'm going to have to use my gas laws. And again, for the temperature over here, when I do that temperature conversion, it's again going to be 25, which is degrees Celsius plus 273 to get that conversion done. All right. So that's the number of moles of the CO2, right? The gas that's formed. And now I want to know how much calcium carbonate does that represent. So I'm just going to put the CO2 in ratio with the calcium carbonate, 0.01 mole in ratio to calcium carbonate in this reaction was so that would be 1 to 1, 0.01 to 0.01, and that would then be number of mole of calcium carbonate is equal to mass over molar mass. 0.01 is equal to mass over, what is that value? Sorry, I think my screen share dropped. Let me just refresh that. All right. Divide that by my molar mass, which is 100. Is that 100 though? Yeah, this is 100. So the mass will be equal to 1 gram. Okay. And that's it. So when it comes to these calculations, please be very, very careful when it comes to gases, because especially in the DBE, you're supposed to do gas laws. You can't always just assume 22.4, right? If there's other conditions given, use the ideal gas equation. Now, if you are in the position where your teachers never taught you this, she's not going to ask that. That PV is equal to nRT, also not in the matric paper. Okay, so if this seems very foreign to you, don't have a panic attack. It's okay. You're going to survive. All right.